So the first specific flavor of aqueous equilibria that we're going to talk about refers to solubility equilibria. And it gets its own special equilibrium constant K that we call Ksp. And the Sp part comes from the name solubility product. The reason it's named solubility product is solubility equilibria are always going to be written in the direction of the solid dissolving. So in the case of calcium sulfate, which is a solid, which I have sort of illustrated here, you get a chunk of this solid, you toss it into water inside of this beaker. The way that we will write the equilibrium for the dissolution of this solid is always going to be solid to the ions. So in this case, it'll be calcium sulfate, solid, and then proceeding to the ion, calcium ion aqueous, plus the anion here, sulfate aqueous. If there required balancing here, then of course we would balance this, but this is as it is. So when we're thinking about the solubility product or solubility equilibria, the way that we write this up is going to be Ksp is equal to the products over the reactants, but again, it's important that you know that this is the directionality we'll always be referring to, the dissolution direction of the solid. In that case, the solubility product is always going to be equal to products times, or products divided by the reactants. In this case, this would be calcium 2 plus concentration. There's no coefficient here. The coefficient is 1, so this would be raised to the first power, multiplied by the concentration of sulfate ion. In this case, again, coefficient here is 1, so this would be raised to the first power. And there's no dividing by the reactants because the reactant here is a pure solid. And remember from previous video and regarding the sort of semantics of equilibrium constants, we do not include pure substances like liquids or solids in the equilibrium expression. So this will always be the generic format of any solubility product or any equilibrium that refers to the dissolution of a solid compound. Regarding solubility then, if we think about the actual mathematical or algebraic implications of this, what this means is the amount of the calcium sulfate that's actually going to dissolve in this case is always going to proceed until the products of the concentrations of their ions, or the weighted products of the concentrations of their ions, are equal to some constant. That's what it really means. So we could use this expression to determine how much or what mass of the original solid is going to dissolve given a certain volume of water or a liquid here. So using that reasoning, we can also think about an expression like this with respect to Le Chatelier's principle. So what happens if this is true, right? If there is, this is a constant number, it's just a number, meaning that the concentrations multiplied by each other, the product of the concentrations has to give rise to this value. What happens if you artificially increase the concentration of, say, calcium by adding another calcium-containing species? We call this the common ion effect, and what that would look like is a decrease in the solubility of calcium sulfate as we increase more calcium in the system. So the example could be like if we're adding calcium chloride to the beaker. So we've got, some more calcium chloride over here, which we know is going to dissolve into calcium ion, meaning we get more calcium ions simply coming from this, but the chloride doesn't impact the solubility, at least from the common ion effect. And then we think about the solubility of the calcium sulfate on this axis. If we have 0 calcium being added from another substance like calcium chloride, then we have the sort of maximum solubility of calcium sulfate. But as we keep increasing the concentration of calcium from this exogenous salt, this other thing, then what that does is it artificially drives up this calcium concentration, which means that this sulfate concentration has to go down to ensure that this constant value is maintained, right? You can't change that. The product of these two concentrations has to remain fixed, has to equal a constant at equilibrium. So if you crank up calcium by adding something else, sulfate has to decrease. How do you decrease the concentration of sulfate in the solution? Well, you have to drive the equilibrium backward, meaning you're producing more solid, which means less solid is soluble. So what we would see is this sort of parabolic or hyperbolic decay of the solubility of calcium sulfate as we increase the concentration of calcium. The same thing could be true if we were adding, instead of calcium chloride, maybe we were adding, say, sodium sulfate, and in this case sulfate is going up, and that drives calcium back down. The same effect would be observed there. And we call this, again, the common ion effect. And so the common ion effect is really just a specific application of Le Chatelier's principle as it pertains to the solubility of a solid, specifically an ionic solid. So of course solubility equilibria, amongst many of the aqueous equilibria we'll talk about in this class, had a big impact in Flint, Michigan during the water crisis, and continues really to have a big impact. And Flint is not alone in this challenge. This problem is actually ubiquitous across the entire world. In the United States alone, it's estimated that about 20% of all adults consume drinking water with lead 2+ levels that are in excess of the EPA lead and copper rule, which, based on health standards, suggests you shouldn't drink water in excess of 15 parts per billion or micrograms per liter. So that's 1 in 5. If you look globally, though, you can see that well over a quarter of the entire world water supply suffers from elevated lead concentrations in water. One of the major contributing factors is that lead is a really easy metal to work with, and it's super cheap, and it's fairly abundant on Earth. And so it has been used for the better part of a little more than a century as a service line, as an actual line to deliver water to homes and to store water. And that may sound crazy to you, because we've known about Mad Hatter syndrome, we've known about the effects of lead for a long period of time. So why do we send water through those service lines? And in fact, Colorado Springs has many lead service lines. Denver has even more. Virtually every city on the eastern seaboard and in the Midwest contain lead service lines, especially the older parts of this country. So why do we use them, knowing that it's dangerous? Well, it turns out that it's not dangerous if you're careful about the aqueous chemistry. And so traditionally, if you're going to use lead service lines, you typically want to use this thing called corrosion inhibitor. And the most common one to use is phosphate, or some people will call it orthophosphate just because it's PO4 3-. But you can see that in this little cartoon here. And the idea is that this phosphate, because it's a PO4 3-, you know from your solubility rules, the larger this charge, the less soluble the resulting ionic compound will be, in this case lead phosphate. And so what people have done for years is treated drinking water with low concentrations of phosphate, because at certain low concentrations you can't taste it, and they don't have any health effects on humans. What that does is, if the lead pipe starts to dissolve and turn into lead 2+ here, then it immediately reacts with phosphate and drives the equilibrium back this way to form this lead phosphate compound, which is denoted by this sort of brown hue. And people call that the mineral passivation layer. And what it really is largely lead phosphate in this form. What's cool is that this solubility product, I can't remember exactly what it is, but it's on the order of like 10 to the minus 34. So it means that together the lead concentration multiplied by the phosphate concentration is abysmally small, right? So as lead increases in concentration, right, this whole reaction shifts to the left to maintain this constant, which is tiny, which means that there can be very, very little free lead concentration as long as you maintain even a little bit, a non-zero amount of phosphate. But if this thing starts to go to 0, then the lead concentration can rise quite a bit. And that's exactly what happened in Flint and what's happening in several cities across the US is if this concentration starts to plummet, what happens is the lead concentration has to rise in order to still satisfy this equilibrium. How does that rise? Well, you start to dissolve some of this scaling, this mineral passivation layer, which liberates more lead 2 plus into solution. And so what happened in Flint is over the course of about a century, the city had been using orthophosphate as a corrosion inhibitor, and they developed this nice scaling that you see down here. These are the pipes. They don't look particularly tasty to drink from, but that's how most of your pipes look. You just don't get to see them. And they've got this nice mineral passivation layer. But as you imagine, if you stop using orthophosphate, which is what the city decided to do when they switched water supplies, then this concentration plummets, this stuff, the scaling starts to dissolve, and you get some lead in the drinking water, which can be bad, but it's still going to be fairly low if you're just dissolving the scaling. The problem is once all of that scaling dissolves, then you're exposing raw or bare lead metal to the solution or to the water. And then it starts to leach much faster. And that's when you get really elevated levels of lead because your passivation layer has completely dissolved. So that's exactly what happened in Flint. So if we were to write this up just to illustrate what a Ksp expression would look like, or an equilibrium expression would look like, remember Ksp in this case is going to be equal to the concentration of those two ions raised to their respective coefficient powers. So this is going to be lead 2 plus to the third, and then phosphate 3 minus squared. And those products, those weighted products, have to be equal to 10 to the minus 34 if the system's at equilibrium, which it's always striving to do, right? So you can imagine if you spike your system with a certain level of phosphate, that's going to drive the lead concentration down in order to still maintain 10 to the minus 34. And so in a worksheet that you're going to walk through, you're going to go through a series of scenarios in the Flint system, in the Flint case, where you can really compute then what's the minimum level of phosphate ion concentration that a city would need to maintain to keep the lead 2 plus concentration below 15 parts per billion, right? So it's a computation as simple as that. And what's really nice about thinking about things in this way is you're thinking about Ksp less from a perspective of something dissolving and more from a perspective of a controlling parameter in water quality. So how do we use this expression, which is exactly what water quality chemists would have to do, how do we use this expression to compute how much of this stuff we need to add to a city's drinking water so that we don't poison them, but we also keep the lead down below 15 parts per billion. What we'll talk about in subsequent videos in this class is equilibria in aqueous systems isn't this simple. And in fact, there's all sorts of other junk that's going on in the system, and almost all equilibria are connected through one means or another, through pH, through other competing equilibria, etc. And so this is the simplest consideration, but then we're going to add more and more complexity to the system as we consider parallel aqueous equilibria that are occurring in the system.